Well, good evening all. You are welcome to the tutorials with From Eternity the Schoolboy. Today we'll take a look at chemistry. In our last class, we ended the last topic with what? Separation techniques with what? Chromatography, right? So we said that in today's class we'll start with atomic structure and what? Atomic structure and what? Bonding. We'll look into the atom, dissect the atom. This will take us a couple of weeks. We're going to do a lot of things under this topic. We'll start from brief history, not a complete, just a brief of different scientists that worked in what? Atom, that contributed in one way or the other in atomic structure. Discovering what actual structure of an atom is like. We'll mention few of them, at least one or two things concerning when the experiment they conducted, and what have you. Is this your notes?
I don't see if I brought any about this.
You not see your notes? Hey, students, oh, answer me. You don't see your notes. Let's continue. Now, without wasting time, I wouldn't want to go into long story of the people that worked doing the ancient Greek and what have you. I just want to start from John Dalton, okay? I want to start from who? John Dalton. What John Dalton actually did. Actually, John Dalton proposed a theory known today as what? Dalton's what? Atomic what? Theory. John Dalton proposed what? A theory known as what? Dalton's what? Atomic theory. You know, I told you that ancient Greeks, that they were the first, actually they were the first, ancient Greeks were the first to use the word what? Atom. Okay? Ancient Greeks, they were the first to use the word atom, and it actually means indivisible anyway. But nothing much was done until John Dalton, an English chemist, took it upon himself to come up with a theory to describe the nature of what? Atom. So, let's go to what John Dalton did. Actually, that was in 1808. In 1808, John Dalton, an English what? Chemist, proposed a what? Atomic what? Theory. I'll just give us a summary of what the theory is all about. A summary. So this is the summary of John Dalton's atomic theory. According to, remember our scientific method, right? We said that after hypothesis, you go down to what? After observation, right? You observe, then put forward an hypothesis. Then you test the what? Hypothesis. If the hypothesis is in line with the what? Result of your what? Experiment, then you can move to what? Theory. Other scientists will now look into it too. If you say the same thing, it will go to theory. And if you consistently show the same result, it will move to what? Principle or what? Law. But if your work is not give a different result, if the result of the experiment is not in line with your what? Hypothesis, that means your hypothesis is what? False. It can be rejected. You go back and look at your what? Observe again and come up with another what? Hypothesis, and keep doing like that. So this is what John Dalton did. He actually got to the level of theory, and that is the theory I want to outline now. Number one says that according to John Dalton, number one, all elements are what? made up of what? Small indivisible particles called what? Atoms. So he's in line. He actually agreed with ancient Greeks that say that atom is what? Indivisible. So that's what John Dart, number one, he said that all elements are what? Made up of what? Small indivisible what? Particles called what? Atom. Now the second part of the theory says that atom can neither be what? Created nor what? Destroyed. Atom can neither be what? Created nor destroyed. He also said that the atoms of the same elements are alike in every aspect and differ from atoms of other what? Elements. And atoms of the same elements are alike in every aspect and differ from atoms of all other what? Elements. So he also went to say that doing the fourth one, the fourth one says that when atoms combine with other atoms, they do so in simple ratio. The fourth one, when atoms combine with other atoms, they do so in simple ratio. Ada, are you okay? It's not why. Huh? Stand up and walk around so you can get yourself. Oh? He said that when atoms combine with other atoms, they do so in simple what? Ratios. Now the fifth one said that, the fifth part of it, theory, said that all chemical changes result from combination or separation of what? Atoms. All chemical changes result from where? From what? Combination or the separation of what? Atoms. All chemical changes result from the combination or separation of what? Atoms. So this is what John Dalton, a summary anyway, of what John Dalton proposed in 1808. You know, one thing about science world is that once you come up with something, bam, all eyes will do what? Will be on you. They want to find out, is it true? Is it really true? Some want to find out whether it's true. Some want to find out if there is something else they can add to that thing you did. Some want to find out. A lot of people with different interests will start looking at your what? Work. So over the years, a lot of scientists started looking at what, because since the ancient Greeks say what they said, nobody has done something so serious until this man came up with this theory. A lot of them started looking at what he said. Is it true? Is atom truly indivisible? All those, this is what they started carrying out. They started doing their what? Experiment, and some may just be doing one thing on their own. They did a different thing and discover that some part of what that is said is not actually what? True. So that a lot of, in fact, the theory, in fact, that theory, in fact, is almost did not fly. It had a lot of what? Modifications. It had a lot of what? Modifications. But the man did a great job. At least he gave room for it helped others to look into it. True of us. If you didn't go to that extent, they will, even if yes, a lot of greater part of it met modification, a lot of modification, but still, till today, you cannot talk of atom without talking about who? John Dalton. So he's a great man. A great name, John Dalton. Now, so because of a lot of things, a lot of his work, part of the theory did not actually fly well with some aspect of what? Sciences, chemistry. Like some could not, some part of it could not explain electrolysis, and other aspect of what? Matter. What other processes matter undergo. So now let's look at the modifications. Let's look at the part of the theory that was modified. We are modified, and the one that were retained. Now let's look at the first one. The first one say that all elements are made up of what? Small what? Indivisible particles called what? Atom. Good. By the time we get to Lord Rutherford's work in atom, you understand better why this first part of the theory was modified. This statement was proven wrong. The work of Lord Rutherford proved this statement wrong, because from the work of Lord Rutherford and his boys, I will say boys, because Lord Rutherford na boss in B that time, na boss. He has laboratory, he has scientific lab where he has a lot of people, young scientists working under him. You can Google about Lord Rutherford online. You read a little of this history. You appreciate what you're studying. Okay, you appreciate the topic well. You read about him, and if you see young scientists that we are working under him, some of these names you hear now worked under him that time. He has a lab, very big lab. So most of the things they discovered, most of these boys, most of these young scientists that discovered most of the things, we are working under him. So he's as good as supervised almost all their work. That's why that somebody that was arguing with me sometimes. Anyway, it's not argument. He was saying what he read, but he didn't really understand, because he didn't know the historical background of what he read in the chemistry textbook. He was saying that it was Lord Rutherford that discovered neutron. I think one of my students, he was saying it with seriousness, because Lord Rutherford was almost most of the day we are working under him. So he's as good as maybe he worked with them, But the point is that the person that discovered neutron, I will talk about that one when we come. Even though Lord Rutherford mentioned something, but he didn't call it neutron. He considered that there's something else inside the nucleus that has the same mass with proton and no charge. He didn't call it anything. He just suggested that it was after around 1932 that Chadwick now worked on it and actually discovered that thing Rutherford said is true. There's something here. It was Chadwick that called it what? Neutron. So it was actually Chadwick that discovered what? Neutron. But if you're not careful, you think that it's who? No, don't worry, we'll get there. Let's continue. Now, see what happened there? So the work of Rutherford in the structure of the atom actually opened our eyes that atom has other what? Particles, particles. We call them what? Subatomic what? Particles. And the prominent of them are what? Protons, what? Neutron, and what? Electron. Okay? Remember, Dalton's first part said that all elements are made up of small, indivisible particles. But this one is stating that no, atom has sub-particles. It's not indivisible. Okay? There are other sub-particles under what? In atom. So how can it be what? Indivisible. So that's why this one was what? Modified. That's why this one didn't fly. Because of the presence of what? Protons, neutron, and what? Electron. So how can you say that atom is indivisible when it has these things. Does it make sense? Does it make sense? So that's what where this one had issue. That's why it did not fly. So an atom is not an indivisible solid piece. It has some things inside it. It has particles inside it. Prominent of them is what? Protons, what? Neutron and what? Electron. So how can you say that atom is what? Smallest, indivisible. No, now it's not the smallest. Is it the smallest? It's not. Now let's look at number 2, where John Dalton said that atoms can neither be created nor destroyed. For those that have read nuclear chemistry, radioactivity, nuclear fission, right? Nuclear fission, nuclear fusion. Can you create an atom? Huh? Nuclear fusion. In nuclear fusion, nuclear fission, an atom can be divided. True of us? You can destroy an atom, true of us, and form different what? Atoms. But not through ordinary chemical what? Reaction. Nuclear reaction. You see that in what? Nuclear reaction. In fact, I gave people one in assignment, chemistry assignment review for tomorrow. Is it tomorrow? No, Thursday, right? That one go loud. 20 questions, right? 24 questions, right? That one go loud. You have now and you have tomorrow to look into it. That is, you see the structure, you see a nuclear reaction there. You see that atom can actually be what? Destroyed. So that has proven that atom can be what? Destroyed. In fact, doing nuclear reaction, nuclear fission, uranium 235, we'll see discuss it anyway, can be splitted into what? Smaller what? Atoms. So why would we say that anyway, this is what he said then. He didn't know that it was through the work of others that came after him that discovered that this atom can actually be what? Destroyed. It can also be what? Created. So you can create atom through, of course, if you destroy a bigger uranium, you create new smaller one. True of us. Then if smaller one come together in nuclear fusion, they can create a bigger one. True of us. So atom can be created or what? Destroyed. Now, another one. So that's why this one did not fly. The third one say that where he said that atoms of the same element are alike in every aspect. Now, every aspect. That's what John Dalton said, and differ from atoms of all other what? Elements. So with time, discovery of isotopy, discovery of what? Isotopes, right? Prove this one what? Wrong. Because isotopes are atoms of what? The same what? Element, but they differ in what? Mass what? Because of what? Difference in what? Difference in what? Neutron. This is a jam question, no, please. This is a jam question. Reason why they differ in their mass number, because of difference in their number of what? Neutron. They have the same number of proton. True of us? Yes. Because they are chemically, their chemical properties is same thing. It's just their physical what? Properties. But John Dalton say that they are like in every aspect. Yeah, every, which is not true. Yes, they have the same chemical, they chemically alike, but physically they are not. Because they can never, in fact, the density will not be the same, because their mass, I told you, mass is not the same thing, density will not be the same thing. A lot of things that have to do with physical properties will change. So that's why this one did not fly. That's why this one did not fly. So you can have chlorine. We have chlorine 35. We have chlorine 37. True of us? Good. How many atoms like that? Now, that's why the third one did not fly. Let's look at the fourth one. The fourth one says, when atoms combine with other atoms, they do so in simple what? Ratio. when atoms combine with what? Other atoms, they do so in simple ratio. Remember when we discussed compound, we said that compound results from combination of atoms, right? Bond formation, right? Good. And every compound, atoms that form a particular compound are actually combined in a fixed what? Ratio. In a fixed what? Ratio. No matter where the source of the compound, so far is this compound, so far it is sodium chloride. Every sodium chloride, sodium and chlorine must combine in ratio of 1:1. No matter the source of the water, so far is water. In water, hydrogen and oxygen must combine in ratio of what? 2:1. Now, that's the fixed ratio. But John Dalton told us that these atoms are combined in simple what? Ratio. Simple what? Ratio. That's where the problem. That's where the problem now ensued. So with time, it was discovered that this one is actually for what? Inorganic what? Compounds. True of us. Inorganic like compounds like water. Can name them. Sodium chloride. Small ratios. When you go to organic compound, you see organic compound. You see ratios. You see some sugar having 22 carbon atoms. True of us. You start seeing different compounds with different their ratio, very compound ratio. True of us. So that one is for what? Inorganic what? Compound, not for what? Organic what? Compound, like proteins, fats, in chains, polymers. So the monomeric unit of polymers, they combine in simple ratio. Thousands of chains of carbon. True of us. DNA, nucleic acid. Do you know, nucleus is a giant molecule. DNA is a giant molecule. Do you know the ratio? So that one did not fly. It's only for what? Simple inorganic what? Compound. Not for what? Organic what? Compound. So that's why this one did not fly. This fourth one did not what? Fly. Even some organic compounds, even some inorganic compounds are not even combined in simple ratio. Some form complexes. True of us. You know what complexes are, right? No, by the time we enter bonding, then or you can also see them in salts. Then we'll talk more on that. Let's not waste time there. Okay, now let's look at the fifth one. It's only this fifth one. That did not undergo modification. It says that all chemical changes result from what? Combination of what? Separation of what? Atoms. And it's true till today. You can't talk of chemical change without bond formation, right? True of us. You can't talk of chemical change without what? Bond formation. And bond formation and breaking of bond. In fact, chemical change is all about what? Bond formation and what? Breaking of what? Bond. And you can't talk of bond formation without talking about what? Combination of what? Atoms. True of us. Is atoms combining together that they form the bond. It's not true. And if you want to break a bond, if you want to separate atoms, you break their bond. True of us. They go their way. True of us. That's why this last one is still relevant to today. Okay. So that's John Dalton for you. Any question on John Dalton's work? Any question on John Dalton? If you have a question, we go to the next scientist. We go to the next what? Scientist that worked, do one or two things on the atom. Now, in 1885, in 1885, X-ray was discovered by Roentgen. I don't know how to pronounce this name. It don't sound English to me, and I keep saying that I'll look it up to what is it called? Let me write on the board. Maybe someone here may help us to pronounce it. Look at it. I'll say I'll look it up. Years will pass. I will not do that. Roentgen. Who has this? Let's even do it now. This, what is it called again? Huh? Can you check? Okay, check your phone. Okay, no, huh? Google what? Okay, is that what you want to do? And then, do it. Why you continue? Is that what they are doing? Do it. Let's see how they pronounce it. Google has this pronouncing this thing. I think it's also an app, right, on its own, right? Right? It's also an Let me see. What?
Electrostatic unit of electricity and 1 cc of dry air.
Tafia, what's the name?
Röntgen.
Okay, again. Again.
The dose of ionizing radiation that will produce 1 electrostatic unit of electricity.
Röntgen. Röntgen, I think so. Röntgen, yes. Röntgen. He's one that discovered X-ray. Okay, now let's know our time, please. Let's continue. Röntgen, yes. I used to call it Roentgen. Since secondary school, I was just calling it Roentgen up and down. I didn't bother to look it up. I will say I will look it up. Today, I've not done that. I say it was end today. Before I embarrass myself one day. Röntgen. Let's continue now. So he discovered what? X-ray in 1885. So in a discharge tube, he realized that we mentioned that we have not even seen this part of the world, a very funny part of the world. Child, discharge tube. I've not seen it though, but you know it exists. It's well. Let's continue. It's well. So in a discharge tube, the demand I just want to describe how he discovered the X-ray. Yes. He was working with a discharge tube. Now, when electron collide with the anode, he discovered that a particle with high energy and high penetration emerged. He just called it what? X-ray. You know that X-ray has a very high energy. In fact, X-ray can There is nothing it cannot pass through. Are you aware? By the time we go over to the work of Gege and Marsden and other scientists, you understand better what a discharge tube look like. But just know that in a discharge tube we have the cathode. Hello, in a discharge tube we have the cathode and the what? The anode. So the electron came from where? The cathode. That's where they call electron cathode what? Rays. Came from the what? Cathode. That, but when the cathode collide with the anode, a highly penetrating energetic penetrating radiation came out, and he called it what? X what? Ray. That's just a summary of what happened. I'm not going deep into that, but if you want to get more information, you can just Google it. I think David mentioned itself in that thing you're reading, in that thing you played, the work he did. It was it's not. It was what is it called? It was way detailed in what she showed us now. Now that what happened when, so actually you will be asking your exam who discovered X-ray. Is who? See, Jam and Wayek asked this question. So I don't know if you have seen it in past question before. They asked, the one I've not seen it is the year, but I've seen their name. They'll ask you who discovered this. They will list their names for you. So you know that we are not just talking history here. We are talking, that is what you see in your examination, not just history. But why it's good to mix it up is that you help you to talk about a bit history of how it happened. Is that it help you to do what? Appreciate what you are what? Doing. Now that's what happened in what? Okay. High energy penetrating. Penetration. You know, I told you that X-ray, that not X-ray cannot what? Penetrate. It's a powerful radiation. Are you now? Let's continue. So now in 1897, huh? X-ray gamma rays. X-ray now. Yes, now. Okay, you think gamma ray has more? Yes. Explain. Huh?
When you talk about gamma ray, now I remember it's between alpha, beta, and gamma ray under nuclear fusion.
There's something I want to teach you. Before you say that what somebody said is not true. Try to wait. No. You said you ask a question. You said that gamma rays penetrate more. That's what you said. No, I ask you now. You said yes, that is penetrate more. That's why I came closer. So you can teach me. In case, see, I'm not saying that I'm not. See, you can never see. There's a system I use here. If you notice that, I cannot tell that what you said is wrong. It's when you cannot prove what you said. That's when I'll say that is wrong. So if you say that it penetrates more, then let's know how it penetrates more. Does gamma ray has, which of them has let's continue. Now yes, browse now, gamma rays and X-ray, which one penetrates more? While we continue. It's not so rich. So let's continue. In an age A3, use A3 to. Oh no, just check it up. Let's continue. So in 1897, J.J. Thompson came up with his own. In fact, J.J. Thompson did. In fact, he laid foundation for a lot of things in the atom, in the structure of what? Atom. Starting from the electron down to proton. Even he tried to even talk of, he tried to tell us what atomic structure look like, but he didn't. He did not conclude that because of the work of Rutherford and his boys. Now look at this. Look at what he did. In 1897, he actually discovered electron. Actually discovered electron in 1897. First of all, he discovered it. He called it cathode rays, and later say that even though there was some speculations and some suggestion about electron in the past too, but when he now did his work and called it cathode rays, he now compared the properties of the cathode rays with what has been. That was when he now concluded, that confirmed that this is what? Electron. Then other scientists started working on the side, the charge, and what have you. Have you seen anything? Okay, now let's continue. Why should check? Listen as you do that. Now see what you know that I want you to know that under normal circumstance, gases under normal circumstance, they do not conduct electricity at ordinary what? Air pressure. That's why we say that you cannot just call gas conductors on a normal. They do not conduct electricity under what? Ordinary what? Air pressure. Now, for you to be able to achieve that, you must make some changes. And the changes you need to make is that you have to do what? Introduce a potential what? Difference. Okay? Once you put the gas in a chamber or in a tube, you try to introduce a what? Potential what? Difference. And if you do that, then there is high tendency for the gas to do what? To do what? Conduct electricity. Not just that, you also do what? Reduce the what? The pressure. So at low pressure and at a potential difference of about 5,000 volts, the gas can do what? Conduct what? Electricity. The pressure can be as low as 0.0001 watt at atmosphere. 0.001 atmosphere. And if that happens, you see that the gas will maybe start what? Glowing. Actually, this is what he did. J.J. Thompson, in a chamber, in the tube, in a glass tube, he introduced potential difference of about 5,000 volts, and reduced the pressure of the gas to about what? 0.0001 watt atmosphere. The gas started what? You know what I mean by glowing? Do you know? Who have seen fluorescent tube here? Fluorescent tube. I don't think it's no longer. Oh no, it's still. People still use it. Still use it too. Wait, you don't see fluorescent tube. Hey, in the generation. Wait, it was here before now. And it was removed and they put this in. This thing, that thing that is long like this. Some we are long ball. That is fluorescent tube now. Does it have bulb inside? This is a typical example of what you talk about glowing. You see how the thing come up. You glow with a particular what color. Okay? Now, and if it glow, it will illuminate they what? Surround him. So that's what J.J. Thomson now did. What he did is that he reduced the pressure to about 0.0001 atmosphere, and the potential difference of about 5,000 volts. He now realized that the thing now began to do what? Glow. He later increased it. When he increased the potential difference to about 15,000 volts, from normal glowing, it turned to what? Bright green. Bright green what? Glow appeared in the glass. What do you see?
X-ray are like from process outside the nucleus, but gamma rays originate inside the nucleus. They also are generally lower in energy.
Which one is lower in energy?
And therefore less penetration.
Which one is less?
Is X-ray. But there's why they say that gamma rays has shorter wavelength.
X and gamma ray have the same basic properties. They also generally lower in energy and therefore less penetrating than gamma rays. Okay, X-ray can be produced naturally or by machine using what? Electricity. Okay. You are correct. She said that, but it's true. Let's look at it critically. You know that X-ray is used. You can be exposed. It's correct. She's correct. You can be exposed to what? X-ray, even though too much of it is not good for you. Okay, but gamma rays we do what? Melt everything and it just deal with you. You can't even try it with gamma rays. You are correct. For what? So see of RC. See,
But here they say why X-ray are highly penetrating. See, X-ray photons are highly energetic and have enough energy to break up molecules and hence damage living cells.
Yes, too much exposure. But on a normal, I have done X-ray here now. It's X-ray. It's X-ray. They use it to check the structures in the body. True of us. Yes, but too much is not good to be exposed to it for a long time or all the time. Just once in a while, if necessary. Because it can also do what? Damage. But you can compare it to what? Gamma what? Rays. Okay? Yes, they are. They are, but two of them are the most. But gamma rays is more. Is I've never seen that. If you want to go to radioactive whatever, you do what? You cover yourself well against those rays. Okay, but. Indiscriminate exposure to X-ray is also a problem too, except for medical purposes. And even that medical purposes just once in a while. Just once, it's not just small time. You go to X-ray. No. That one I did here. That was the first time I did X-ray in my life. So they are both destructive, but gamma rays. That one is nuclear. That one is what? Nuclear, and you should not even go close to that one for any reason. Okay. I like reasoning. I like what? Reasoning, not just that they. Okay, let's not waste our time. I think our time is almost listed. You have been doing like this since this. What is it? Is that why you have been distracting me because you're hungry? Go and eat now. Okay, she must go with you before you can eat. Ada is not dying. Ada is not dying. Okay. So we stopped at where? Work of J.J. Thompson. We are discussing what J.J. Thompson did in what? To discover what? Electrons. To discover what? Electron. So he now discovered that, he now started asking himself a question: what caused that glow? Why did this glow in this tube, in this glass? Why the glow? So that was where he now came up with the fact that the glow actually, as you reduce the pressure, introduce potential difference. A ray, some rays emanate from where? From where? The cathode, and they travel in a what? Straight line. Travel in what? Straight line. So he now started describing the properties of these what? Rays. Because they came out from where? The cathode. He called them what? Cathode what? Rays. He called them what? Cathode rays. So he now started doing other experiments to actually study the properties of these what? Rays. So that's how he came up with the properties of what? Cathode rays. Put it down, please. He came up with properties of cathode rays, and the properties are as follows. One is that they travel in what? Straight lines. They travel in what? Straight lines. And they cast shadow of any opaque object in their path. They leave the cathode, they travel in straight line. If there's any opaque, you know what an opaque subject is? Object is. Any opaque object in their path, they cast the what? They cast the what? Their shadow of any opaque what? They travel. He came up with, no, he said that what caused the glow is made of rays that came from where? The cathode. And that rays that came from the cathode, he called that rays what? Cathode what? Rays. He now further experiments, to now determine the properties of this what? Cathode ray. He now studied the cathode ray to know what they are. So after the study, he now came up with these properties of cathode rays I want to call out now. Properties of what? Cathode what? Rays. Number one is that they travel in a what? In a straight line, and cast the shadow of any opaque object placed in their what? Path. Any opaque object placed in their what? Path. Then number two is that they are what? These rays composed of mainly negatively charged particles. They are composed of what? Negatively charged particles. Negatively what? Charged particles. And they are capable of what? Producing mechanical what? Motion. From electro, they can create field, a field. Let me not go into field. Just know that they are capable of what? Producing mechanical what? Motion. Mechanical. All right. This will be a kind of how do I put it? A kind of a forerunner for what you see in electric field, okay? Field from electromagnetic, from electrical to what? Mechanical, okay? Let me not go. That's why I said I don't want to go there. To take us to another thing. Let's just take it at this level. Because at this point here, at this point, I'll call up the electron. He just called it what? Cathode. He just noticed that they can do what? That they can do what? They could do what? Produce what? Mechanical what? Motion. He didn't know what they are. We at that point in time, he was just describing the properties of the rays that came from where? Cathode. So another property he noticed is that they are what? Identical in what? Nature. They are what? Identical in what? Nature. And the ratio, their mass, they are charged to what? Mass ratio. They are identical in nature, and they what? And in their what? Ratio of charge to mass. You know, they can come from different sources. And you can use different type of tube, different type of gas in the tube to produce the what? The ray. But irrespective of the nature of the gas you used, the tube or whatever you are using, the same rays produced have identical. Use this gas, use the other gas, use this one. The ray have the same what? Rays have the same what? Properties. They are identical, even in the ratio of what? Charge to what? Mass. So that means it's a fundamental what? Particles. Am I communicating? That means it's a what? It's a fundamental what? Particle. Let me not go far. So that's what he now realized, that they are identical in nature, and the ratio of charge to what? Mass, irrespective of the what? Residual gas in the tube or the metals used as the what? Electrode. No matter what you use as your electrode. Remember, we have the two. We have the cathode, the electrode, and the gas. No matter what the type of gas you use, no matter the electrode, the metal you use, they will still produce these cathode rays, and the cathode ray that will produce is the same properties they will have. So this is why Thomson now argued that these particles were what? Fundamental what? Particles. That means every element has this what? Particle. That's the meaning of fundamental what? Particles. It's fundamental to every what? Element or atom. Am I communicating? That's what he concluded. Of the electrode used. You know, metal, you can use different metals as electrode. What? The nature of the metal you use doesn't matter. It doesn't matter the gas in the tube. The rays that will produce is always have the same, identical, and the ratio of their charge to mass is what? Constant. The same thing. So you know, okay, that means if we use this metal as cathode, use this gas, the same thing, the same rays. That means this is present in all what? Matter. That's what he concluded. Is present in all what? Matter, in everything. That's the meaning. Because matter is what? Anything that you can do what? You can do what? Anything that has what? Sorry. Okay. I wanted to say anything you can touch or feel. Well, no problem. I'll confuse you more. Okay, now. So this now, you know, I told you that before he started his work, a lot of scientists did one or two works in the past. So he was just affirming what they did, making it concrete, confirming it what they did. You know, the issue of discovery is not, is the person that did the final work that they normally acclaim to be the what? The person that did work, discovered it. Maybe the person that started something may not even conclude it. He may do something and stop. Another person may now come in, pick it up, and start working towards it, and do more research on that. Every scientific research started from somewhere. Some other person did what? Stopped. Am I communicating? There is no discovery. I have not seen a discovery where they say that is the person that started it and ended it. I have not seen such. Even this bulb, even the electricity, they say Faraday. If you trace it, someone started something, but maybe couldn't continue before he did what came up. Let me not go there. So other scientists have been talking about it, but in that his work now, he now concluded that these particles must be the electron proposed by others. In fact, at a point, he just concluded and said that this is what electron. That's what he did without wasting time. So now, before we conclude, we stop here. I want to let you know that we just managed to talk about what J.J. Thomson did with respect to what electron. We've not talked about what he did in terms of charge to mass what charge to mass ratio and the work of other scientists. Maybe in our next class we'll continue, we'll conclude what he did with respect to charge to what mass ratio, and we'll now move over to the next scientist. No, apart from the electron, he also discovered what proton using the same tube. He used the same tube, but he changed some things there to that he just changed one or two things and came up with what proton. It was when he now went to propose the model, atomic model, that he could not finish it, because before then, after then, this guy Rutherford, they are aware of alpha scattering experiments. Through his boys Geiger and Marsden, in the alpha scattering experiments. Another work they did discovered that actually, in fact, J.J. Thomson said that when he discovered proton and discovered electron, he now said that he proposed that an atom is composed of a positively proton core with electron embedded in between the charges. That's what he said. That this is how the atom look like. He said that this is how the atom look like. We have a positively charged like this. This is what he said. After discovering proton and neutron, we have electron like this. This is what he said. That means this is how the atom look like. But through the work of alpha scattering experiments by Geiger and Marsden, and the other works that prove that atom is actually composed of electron revolving in a planetary fashion, and the nucleus and all the other part of the atom is empty, nothing inside. It's just something like this, a solid mass in the middle, then and the shell like this, and the electrons are revolving in the planetary. It was Rutherford and his boys that came up with this. So this made this work look as if the guy actually wasted his time, but he didn't waste his time because he gave room for their work. Had it been he didn't do it, they wouldn't have tried to bombard the gold foil to see how it was when they bombarded. I think I'll stop here. I'm going to what we'll do in our next class. Let's stop here so we can go. Any question? We'll start from discovery of proton, how he discovered proton, but we'll discuss the charge to mass ratio first of electron. Then we'll now go over to J.J. Thomson work in discovering what proton. So I think we'll stop here so we can go. In our next class, we continue from there. Any question? If you have any question, please ask. Feel free to do what? Ask.
There's always a God that is a bomb in chemical.
Okay.
Then there's this thing that I want to ask about meshes now.
Okay.
The meshes, when light makes use of light meshes, is a chemical reaction.
Okay.
What is the bond there?
What's the bond there?
Let's say, I don't even know the...
Austin is involved now. Basically. You are aware now? Uh-huh. So the point now is, what is the component of that match? That's what is it called? That end of it, where that end. So the point now is, what is the component? What does it contain? Huh? There's combustion. I hope you know. Are you aware? There's combustion. And without oxygen, that thing cannot work. Two of us. Okay.
That's big stuff, so I don't know this thing that is another one to bring them together. Yes, this comes this about combustion, which oxygen is involved. So this now is that the content of that and the pack.
Okay, what up? I don't even know the content, sir. But I'll find out. I'll find out. Thank you for that question. I will find out. I'm not bothered to look into it, but I'll find out. Maybe tomorrow we'll now discuss it. You can also find out too. She brought in a very important question, and I like it. You can also find out. Okay. Mm-hmm. Any other question? Any other question? All right, thank you very much for today. God bless you.